The path class handles parsing of file names very nicely, thank you, but what about working with files, folders, and their contents? That requires a different set of objects. The system.io namespace provides these objects like drive info for working with a drive. There's file and file info, and directory and directory info classes for working with directories. Why then are there two sets of classes, file info and file, directory info and directory? Well, suppose you want one piece of information about a particular file or folder. You can use the static methods of file or directory to retrieve the information you need. For example, here's code that loops through each directory contained within a directory. Here we're using directory.getDirectories. The getDirectories method is a static method, doesn't require you to create an instance of the directory class. You give it a full path string, it returns back an array of strings, each one corresponding to one of the directories within the directory whose full path you've specified. So you never had to create an instance of the directory class to get this information because all the methods of the directory class are static. On the other hand, if you want lots of information about a particular object, in that case you'll use the file info or directory info object. Here we're creating an instance of the file info class and then retrieving a number of instance properties of that class. Because we're retrieving multiple properties, we wouldn't want to use the file class, because if I use the file class, I'd have to specify the file name for each property I retrieve, and the .NET Framework would create a new instance of the file class for each property I wanted to create. This way, I retrieve the file info I want to work with, and then retrieve the properties of that file info object. So if you need one property of a file or directory, use the file or directory class and its static members. If you need multiple bits of information, use the file info or directory info objects, supply the file or directory name in the constructor, and then you can retrieve multiple bits of information about a file or a directory using the file info or directory info objects. In our sample application, I'll click the File System Info classes to bring up a form which demonstrates behavior of the various File System Info objects. Now, first of all, we have here a tree view which lets me display information about files and folders. We'll look later at how this code works. But for now, to get this list of drives, all we're doing is looping through the driveinfo.getDrives method. It hands us back a collection of drives, and for each drive that's available to us, we add a node to this tree view. Again, we'll look at the code later on. Now, once I select a file, let's go select a file here somewhere. Where are we? Here we are. Say here. We get information about that file. Now, this is not like the path class where we're just parsing text. This is actually looking at that particular file info object. Now, because we're working with multiple properties of the same file, I'm using a file info object and retrieving its various properties. There are properties like attributes that tell us what the attributes of the file are, the creation time, the last access time, and the last write time. There's an extension property, which overlaps a little with the path class, but it gives us the extension and the full name. There's a full name property. There's a name property that gives us just the file name portion. Now, if we were looking at a folder, we would be looking at the parent and the root property, but we're looking at a file, so instead, we have a length property. Let's look at a folder instead. Here, when I select a folder, there is no length. This one has no extension because it just doesn't. But you see it has a parent property, which is its parent folder, and its root property, which is the root of the folder, C:\\. So files and folders, it would look like, really have a lot of the same properties. We'll look a little bit later at how we discern between them. Let's go a little higher up and look at a drive. For a drive, we have a different set of properties altogether. For a drive, the drive info class provides these properties: name, drive type. Fixed could be one of a number of different kinds of drives. I'll try my A drive and see what it says. It's trying to retrieve my floppy, and I don't have a floppy. But if there was a floppy, Windows provides a virtual floppy drive. You'll see that it is removable and it's not ready. Go back to C, it's a fixed drive, and it is ready. And finally, if I go to D, you'll see it's a CD-ROM, and it's not ready. Let's go back to C. We'll see that we have available free space, the drive format, the root directory. These are all just simple properties of the drive info class. There's total free space and total size. There's a volume label property, which we could retrieve if the drive had a volume label. This one does not. In any case, it's very simple to retrieve all of these properties for a drive, for a folder, or for a file within a folder. And there we go. So all of these properties are simple properties based on the file info, drive info, or directory info class, depending on which kind of object we select on this form. In order to completely understand these objects, you have to investigate the hierarchy of these objects. It's a simple hierarchy, and it looks something like this. Obviously, I'm leaving out thousands of objects in the .NET framework, but the ones I care about are object at the root, and then directory, file, and file system info inherit from object. File system info is the base class for directory info and file info. Since both directory info and file info inherit from file system info, you can bet that they have lots of properties in common. The directory info class and the file info class each add a couple of extra properties to the file system info class, but it's the file system info class that provides most of the properties of the directory info and file info objects. The directory and file objects, however, don't inherit from a common base class except object, so their combination is not terribly useful. But directory info and file info, since they inherit from the same base class, make it easy to use both objects in one set of code because you can use the base class file system info as the parameter you pass around from one procedure to another. As a matter of fact, that's how our sample works. The base class, file system info, provides much of the functionality for both of its child classes. It provides properties and methods which are pertinent to both files and folders. The inheriting classes, file info and directory info, each provide their own additional members that supply functionality that a file needs or a directory needs individually from the common features. For example, the file info class provides a directory property and a length property. Directory tells us the parent folder, and length, of course, is the size of the file. The directory info class provides a parent property, which is the parent folder. In addition to the methods you've already seen, the directory class, that is the one where you use static or shared members on a one-off basis, has a couple methods we haven't looked at yet. There is the create directory method and the delete method. The create directory method is very smart. If I say create a directory like C:\A/B/C/D, if none of those paths exist, create directory creates them all. If one of them is missing in the middle, it creates that, and then from then on down. The delete method is very scary. The delete method will delete what you tell it to delete. So if you call delete passing in C:\, stand back, your hard drive is now toast. So make sure you're careful with the directory.delete method so that you don't ruin your entire computer. It's nice that the delete method is so powerful, and to quote a popular movie, with power comes responsibility. It's up to you to make sure that you don't pass in a root-level folder that's going to ruin your entire hard drive. If you ask the delete method to do that, it will be very happy to delete everything off of your hard drive. In our sample, we loop through driveinfo.getDrives. That method returns a list of all the drives on your computer, and we displayed the name property of each drive info in our tree view. That's how we got the drives. We call directory.getDirectories to retrieve the folders on each drive, and we call directory.getFiles to retrieve the files in each folder. We did this recursively to fill our tree view control. In order to fill the tree view, we'll need to use some techniques for working with the tree view control, and although we haven't covered the tree view yet in this course, it's pretty easy to figure out what's going on. We're going to call the add method of the nodes collection of the tree view, and that returns a new node object to us. And we'll also add a filler node as a child, so you'll see a plus sign. The code looks something like this. I call filestreeview.nodes.add, and I give it the text of the node. This comes back to us as a tree node object, and we need later on to be able to tell when I select a node what kind of thing it represents, a drive, a directory, or a file. I've created an enumeration named item type, which has options for drive, directory, and file, and we'll store the value into the tag property of the node. So later on, if we programmatically need to know what kind of object this node represents, we can look at the tag property and see what's in there. In addition, I'll add a new child node for this node. So we'll call node.nodes.add, and I'll call it filler as the text. We'll later remove this node when you try to expand the drive, but unless we put that child node there, we won't have a plus sign. This is probably the way Windows Explorer works, because if you've ever used Windows Explorer, you've noticed that drives always have a plus sign next to them until you expand the drive, and if there's nothing on the drive, then the plus sign goes away. They don't know when they first fill in the tree view in Windows Explorer if a drive or a folder actually contains contents until you expand the node. I'm guessing actually they're using a background thread to go populate that child list of nodes while you're staring at Explorer. In our example, however, we're not going to. We'll just fill the contents of the node when you expand the node, and we'll see how the code for that works a little later on. Clicking a node to expand it in the tree view removes the filler node if it exists, so that extra node just disappears. You'll never see it. It adds a node for each directory within the current file system object represented by the selected node. So if you expand a drive, the code gets a list of all the directories on that drive. If you expand a directory, it gets a list of all the directories in that directory. In addition, it adds a filler child node, so the plus appears next to each of those child nodes. So when we expand a drive, for example, we add a node for each directory, and for each directory, we add another filler child node, so each of them has a plus sign next to it. We'll also add a node for each file contained within the selected folder. So we first look for folders, and then we look for files in that folder. To display information, the after select event of the tree view control allows you to run code after you select a node. In our case, we want to fill in information about the selected drive, directory, or file in the bottom of the form. There's one of two different panel controls that we'll display. One for drive info and the other for file system info. Remember, both the directory info and the file info classes inherit from file system info, so we only need two panels, one for drive info, one for file system info. If you select a drive, we display the drive info one. If you select a directory or a file, we display the file system info one. We'll use properties of directory info and file info to display information in the file system info panel. How do we determine what kind of thing you selected? We'll use the tag property, which contains an item type value that we previously set, to discern between drives, files, and folders. Now we're taking advantage of polymorphism, which is a big word, part of object-oriented programming, to allow us to display information on one panel for both directory info or file info. We have a procedure called display common properties. You pass in either a directory info or a file info object. But how does display common properties accept one parameter of either of those types? Well, display common properties accepts a file system info object, that is the base class. Since we've set the parameter to be a file system info object, we can pass in either a directory info or a file info object. If this is confusing, add the words is a to your thought process. Directory info is a file system info, and file info is a file system info. Because both of them is a file system info object, the display common properties procedure can accept an object of either of those types because it's expecting to receive a file system info object. Well, enough talking. Let's look at the code to see how this tree view control does its job. In our sample project, I'll load up the File System Info class's demonstration, and as the form loads, as you'll remember, we need to get a list of the drives and display them on the form. Well, first we get the current directory. I'll come back to that in a minute. But to get the list of drives, we call the getDrives method of the DriveInfo class and loop through each member of that collection. For each one, we create a new tree node by adding a node to the tree view. We set the tag property to be drive, so we know later on that this is a drive, and you can see the enumeration defined there. And we add the child node, the filler node, so we see the plus sign. We do that for each drive, and there we go. We have our drives with plus signs next to them. Before we come back to that tree view, though, let's look at the two methods of the directory class. There's create and delete. So here, if I want to create a folder, say, let's try again. There we go. If I click Create Directory, the code is going to attempt to create it. I call directory.createDirectory, passing in the text in my text box. And here we go. We've created it. That's it. And now we'll set that text as the text of our delete text box, assuming that's where we want to delete next. Well, we created C:*XYAZ folder. Let's make sure it's there. XYAZ. Believe me, those folders weren't there ahead of time. We just created them. Let me put some text files into this bottom level folder. There we go. And now let's go back to our code and let's delete that directory. The form will ask us if we want to allow the code to delete files contained within the folder. And I'll say no. If I say no, the attempt to delete the folder will fail because the folder contains files. Can't delete it. If, on the other hand, I guess we're still debugging here. There we go. If, on the other hand, this time I say yes, the attempt to delete the folder will succeed. If we go back out here, that last folder has been deleted. We have XYA, but no Z anymore. Let's go back out here, and let's try now deleting this folder. Don't do this, please. Okay, so let's delete the X folder. Again, it's going to ask, do you want to allow files within the folder to be deleted? If I say no, it can't delete the folder because X contains things. I'll say yes. That'll succeed. And we deleted, well, this is complaining because it's displaying stuff that doesn't exist. Let's get rid of that. And let's try opening it up again. And now X is gone. We've deleted the folder. We succeeded. So you can use this technique to delete files or folders, entire folders on your hard drive. Make sure you know what you're doing before you go farther. Now onto this tree view and how it works. We've seen how to fill the list here. What happens if I expand the list? Let's expand C:, and we hit the before expand event of the tree view control. We get a reference to the current node and store it away. And we call the clear method of the nodes in the current node to remove all of the child nodes, and that effectively removes that filler node. At this point, the plus sign's gone because this node doesn't have any children currently. What we're going to do is retrieve the full path of the current node. The full path property of a node in a tree view concatenates the name of the current node with the names of each of the parents working all the way back up the tree. So this should end up, for us, being C:/. If we'd been farther down, it would have been the full path. It's very convenient that they do that for you. Now we'll need to get all of the folders in the current path. We'll call the getDirectories method of the directory class. Given the full path string, this will return a collection of all the directories in the folder. And for each one of them, we'll add a new node to our tree view, set the item type, set the tag to be folder so we can later know that it's a folder, and add that filler node so we get a plus sign. Let's run full speed to here. So now we've handled all the folders. Let's do it for all the files. We'll call the getFiles method, passing the full path string in. That returns a list of all the files in the folder. And now for each one of those, we call getFileName to retrieve just the file name part of this, add a new node to the tree view, take that node, and set its tag to be itemtype.file. So we'll know later that this is a file node. I press F5 to run full speed, and there we go. So now we have selected the C: drive. Here's a list of all the folders, and there's a list of all the files within that folder. If I expand a folder, we'll run the same exact code, except this time we'll be one level deeper in the hierarchy. Okay, well, what happens if I select a drive? Let me go down to, say, D: and select it. At that point, the after select event handler runs, and the first thing we do is take the tag property of the currently selected node and store it away into a variable named item so we know what kind of item we just selected. It's a drive. The handle panels procedure takes that item and, based on its value, shows or hides the correct panel on our form. We want to show the drive info panel and hide the file system info panel. Now, based on the kind of item we got, we're going to call a particular procedure. We'll call the display drive info properties given the text of the current node, D:/, and in here we'll just display the various properties of the drive we selected. Not very interesting for that drive. For C:, the same code runs, but it gives us more interesting information. What if we select a file or a folder? Well, let's select, say, a folder. The after select event still occurs. We come in here and get the type, and this time it is a folder. Handle panels will display the correct panel. We come into the folder information, and here we're going to attempt to do the things that only apply to a folder and then call our common procedure to display everything else. I know for a folder, the length label should have empty string in it, because there's no length for a folder. Next, I create a directory info object based on the full path, which is C:/program files. So here, we get our full path, and we create our directory info. Now, I know that a folder has a parent property and a root property that a file does not. So I'll set those explicitly now, and then call the display common properties procedure. Remember, DI here is a directory info object, but display common properties accepts a file system info object. How does this work? Remember, directory info is a file system info object, so this code runs just fine. Because directory info is a file system info, we can pass it as a parameter. Here we're going to just display various properties that apply both to a file info object and a directory info object. And you see on our form, if I expand it out, that length is empty and the other properties have been filled in. Let's try selecting a file instead. We get to the same place. This time we know that our item is a file, so we come down to our file code. For a file, I know that parent and root should both be empty. Let's get our file info object, and the length label should contain the length of the file, because that's not a common property. That applies only to files. We call display common properties passing our file info object, and this works because file info is a file system info. File info inherits from file system info, and so now we can apply these common properties to our file system info object. Parent and root are empty, everything else has been filled in. So we've used common code working with file info and directory info objects to display information that's common on this form. Everything you've seen in this form applies to any application, not just this one. And I think you'll find it useful to be able to fill in a tree view with information about your file system, and the code you've seen here should apply in that case as well. Of course, your applications need to be able to read and write file contents as well as getting information about the files and directories. To do that, you'll use the system.io.stream class, which provides the most primitive support. It allows you to read and write bytes, and that's it. More often, you'll use classes that inherit from stream, like the file stream, memory stream, and buffered stream objects to read and write from file system objects. Let's try an example that uses a stream class to read and write from a text file. Let's try a demo that shows off using a stream object to read and write from a text file. In our demonstration, we'll start by selecting a file. I'll go out to my root folder, and I have demo.txt here that I'll use. And now I'll click the Fill button to fill this list box with the contents from that file. I have a fill list procedure we'll step into here. Starts by clearing the items from the list, and it uses the begin update method of the list box so that the update doesn't update itself until we call end update. If you're loading a large amount of text into a list box and you don't want it to flash, this is a nice way to avoid that problem. Now, since we're working with files, we should have exception handling, and we do. We'll start by creating a file stream object. Given the file name and the mode we'd like to use, we create our file stream object. Now, a file stream doesn't make it easy to read line by line from the stream. If you wrap a stream reader around the file stream, though, it's a lot easier because the stream reader allows you to read one line at a time. So we create a new stream reader, giving it the file stream object in the constructor. Now, here's what we need to do. We create a text string and make it equal to null to start with. We're going to loop. We'll retrieve a line from our stream reader, and that gives us the text into our text string, and it does. If the text string isn't null, we'll add it to the list box. We'll keep looping while the text string isn't null. When text string becomes null, that indicates we've reached the end of the file, and we can stop reading. I'll loop and finish up with the 5 lines from my text file. Now, just to prove a point, I can alter the file by moving that line, say, there. And now let's click the Save button and see how you might save the file. Well, the first thing the Save button does is display a Save File dialog, which you probably haven't seen yet. The Save File dialog's got a few properties you can set that define its behavior. We set the file name, assuming you want the same file name you started with, which was c:\demo.txt. We show the dialog, and sure, we'll save it to the same place. I'll click Save. It already exists. We'll ask, do you want to replace it? There was a property that said overwrite prompt is true, which asks you if you want to overwrite a file. I'll say yes. And now I've got a procedure which saves the contents of the list box back out to that file name. Save list again creates a file stream, this time in create mode, so it destroys the original copy and creates a new one. Again, we'll create a stream, well, this time it's a stream writer, which lets you write one line of text at a time if you want to a file, wrapped around that file stream. And for each text string in our items in the list box, we'll write a line out to the file. When we're done, we don't have to do anything. Because we have a using block here around the file stream, when we're done with the code, it will automatically close the file stream for us. And now if we open it back up, you'll see that it did save it in the correct order, 1, 2, 5, 3, and 4. So this example shows how you can read and write from a text file using a file stream and a stream reader and writer to do the work. You've seen how to read the contents of a file one line at a time. If you want, you can read the entire file in one gulp using the read to end method of the stream reader. So given a file info, you can even make it easier. If you have a file info object, rather than having to open a file stream, you can use a file info object to just hand you a stream reader. So instead of using code like you saw earlier, where we created a file stream and then a stream reader that wrapped it up, if you have a file info, you can use the file info's open text method to hand you a stream reader. Once you have the stream reader, if you want to read to the end of the file, just use the read to end method. Just sr.readToEnd. This is code you could use then as an alternate to using the file stream and wrapping a stream reader around that file stream.